This last section is going to be concerned with the geometry of how we do our expansions, and you'll see what that means when we get to it. And at the last part of the geometry thing, we can talk about the truncation thing, and that will explain why you will see people saying things like, we're using model T261. You might want to know what T stands for. Occasionally you'll see R138 and you'll want to know what R stands for. The answer is we have to look at the various geometries that are available to us. So let's look at the easy case. And this is as evidenced by almost everything we've ever done in dynamics. And actually, I forgot to say why we're doing this. We're doing this since the variables that we care about are not just functions of x and t, which is what we've assumed before, but of course they're functions of x, y, z, and t. So the time dependence part of the problem is solved now by the expansion coefficients. And we've looked at x, but we haven't looked at y. And so what we're going to do right now is look at the x, y part of the problem. In other words, recognize that our functions, temperature, wind, and so forth vary not just with x, but also with y. I think there are spectral techniques in the vertical too. That sounds frightening to me, and we certainly are not going to talk about that right now. So let's review the geometry that we're going to use. So ultimately, we're going to use spherical geometry and things called spherical harmonics, but they're frightening. So I'm going to creep up on them slowly. So let's think about what we've done with the mid-latitudes in the past. In effect, what we do is assume something called a tangent plane. So the circle is the Earth. There's the rotation vector. Here's the equator. I didn't quite get the tangent plane tangent properly, but close. And so the tangent plane is a flat plane tangent to the planet, somewhere in the mid-latitudes. You can't quite do this at the pole. I'll show you why in a minute. And you can't do it at the equator. I'll show you why in a minute. So in the east-west direction, we can use sines and cosines to describe things, or e to the I m k x kind of stuff. Mathematically, this is the appropriate function to use, or these are the appropriate functions to use mathematically to describe the temperature structure, the wind structure, everything else. And then in the north-south direction, which we haven't talked about yet, we can also use that same kind of mathematical creature. In this case, we would call it, let's see, e to the I n l y. Okay, so little l is the wavelength, excuse me, in the north-south direction. Little n is the wave number that we use. So these are the things that are appropriate to use in this geometry, but not in every geometry. And so in terms of these, we would write temperature as a function of x, y. Well, let's go ahead and go crazy, z and t. Sorry, I ran out of space, but we'll manage. So we would write that this is a sum m equals negative capital M to capital M. And then another sum over a little n equals capital minus n to capital N of e to the I mkx times e to the I n l y. And then we're going to have some expansion coefficients, which now have two subscripts, t, m, n, and might be a function of z. I don't know. This z part, I just threw it in there just to make things look more complicated. That's probably not how we would do the problem, but we can't leave z out, okay? So the point is that on this tangent plane, we can write an expansion, a spectral expansion for what the quantity looks like in terms of e to the I mkx, e to the I n l y. Mathematically, that's okay. So if you want to, you could solve the problem with that as a starting point. Problem is that what we just did for the tangent plane doesn't work for the sphere, and it also doesn't work for other areas of the sphere. So let's see what would happen if we wanted to do a problem at high latitudes, up at polar latitudes. So again, we could think about the Earth. Nah, that wasn't very good, was it? Actually, I think there's a shape drawer in this, but let's do that. So there's the Earth again, and here's my tangent plane again. So there's the rotation vector, and there's the equator. And so all we have now is a tangent plane, but it's tangent to the planet at the pole, okay? The appropriate coordinates to use here, to use in this case, would be cylindrical. Whenever you do a problem, and I believe I said this back in dynamics, whenever you try to solve a problem, first thing you have to think about is what are the appropriate coordinates. And so the appropriate coordinates here are cylindrical, which is r, the distance out from the center. Yeah, that doesn't look like an r, does it? So let me try that again. And then the distance around, which is lambda. And then there's also z. So those would be cylindrical coordinates. Those are the appropriate coordinates to use if you're looking at a polar problem. And guess what? They are also the appropriate coordinates to use if you want to study a hurricane, because to first order, a hurricane is like a cylinder. So suppose we want to write the expansion of something in terms of mathematical creatures. So again, in the east-west or west-east sense, the appropriate functions to use are e to the I mkx, or in this case it would be e to the I m lambda, or something like that. However, if you do the math, and unfortunately for you guys, I have done the math, so I know of what I speak. The appropriate functions to use here are things called Bessel functions. Which are functions of the radial distance outwards. And I'll talk to you about those a little bit more, maybe in class, by looking at the fountain of all knowledge, Wikipedia. But a Bessel function is a solution of Bessel's equation. And when you do the math for a cylinder on Earth here, you come out with something that looks like Bessel's equation. So what that means then is that if you take some field, say temperature, and you want to expand it, let's just go x, y, and t, forget about z here. You're going to, again, have a sum over little m of e to the I k m x pieces. That's from there. But now in the north-south, you're going to have these Bessel function thingamajiggies. And so this actually won't be x and y, will it? It'll be a little r and lambda. So the Bessel function is a function of radial distance outwards. And there's lots of them, so we need another summation here. And I'm not sure what the limits are. And then T, M, N, the expansion coefficients of T. So what I'm trying to get at here is the idea that we've been blithely using sine kx, cosine kx, or e to the I mkx in the east-west direction, and that's okay. But in the north-south direction, you can't make that simplification, and things start to get more hairy. And the hairiest of the hairies is the spherical geometry case. The Earth is a sphere, of course, and so it would make the most sense to use spherical coordinates, but they're mathematically the most complex. And over the years, people have tried simplifications to avoid that. The first one we saw, number 1, which is valid at mid-latitudes, is the easiest, and that's why we do so much of our dynamics on that geometry. What we saw just now is that if we put our flat plane at the pole, we get stuck with Bessel functions. The other area of the planet that people study a lot is tropical areas, and you can take the same kind of approach with a tropical area. You can have a tangent plane geometry tangent to the Earth at the equator. And so if you do your work in this frame of reference, in the east-west, you can still use e to the I mkx functions. The math is okay by using e to the I mkx. But in the north-south, so remember on the mid-latitude tangent plane, north-south, we can use e to the I nly. Polar plane, we have to use Bessel functions. And on the equatorial plane, we are stuck with something called a Hermite polynomial. Hermite, I don't know. Hermite polynomials. So these are going to be some polynomial function of y. Okay, so as you might guess now, there used to be a guy called Bessel, and he invented a differential equation, the solution of which are Bessel functions. Then there was a guy called Hermite, who invented a differential equation, the solution of which are Hermite polynomials. So then when you're doing work down, when you're doing tropical work, if you want to write an expansion, then your expansion looks like the same sum as usual over m, and now a new sum over n of e to the I k m x in the east-west direction times some Hermite polynomial in the north-south direction, and you have multiple of these times expansion coefficient m, comma, n, which is where your time dependence has vanished. So what this is leading up to then is the dreaded case of, the full sphere. And most textbooks will jump straight in here. So let me just change the screen and I'll do that. Okay, so, oh, sorry, my bad. Click, 1, 2, 3, 4, 5. So on the sphere then, which is what we're stuck with, uh, the appropriate functions to use in our expansion. So if we decide to use the spectral method and we do an expansion, the appropriate functions to use, and I'm using page 45 of the textbook. So I think I will just put time in here since we have time. Well, let me write this down my own way first, and then we'll rewrite it the way Warner has it. So you have a sum over m, as before. So the m direction represents the west to east part of the problem, and the n direction represents the north to south part of the problem, and we're going to have to worry about the limits of m and n and also what they mean in a little bit. So we'll have our weights, which are going to fade into insignificance for just a little bit while we figure out the rest of this, multiplied by the rest of this, which is an e to the I mkx piece again. Times a piece that we call p sub n m, which is a function of latitude, which is written like this. So mu is sine latitude. So I made a mistake at the beginning by talking about x and y, because what we really have now instead of x is longitude, lambda, and latitude, either phi or this thing mu here. So, oh no, that's not right. That's, change the color. Sine of latitude is this thing, mu here. There's a lot of different notations here. There's one that I'm used to, which isn't the same as what Warner is using in the book. So this thing here is called a spherical harmonic. And so you'll see people say that we're going to do the expansion in terms of spherical harmonics, where the east-west part of the spherical harmonic is exactly the same as what we've seen before, but the north-south part of the spherical harmonic, by the way, that should be, let's change the color here. This thing here should be M. It's just M, little n down here, and I'll tell you what it all means in a little bit. Anyway, so for the sphere, so if we're going to use spectral methods to solve the equations of motion on the sphere, instead of expanding as sines and cosines, we have to expand in terms of these things called spherical harmonics. If we have a look at Warner, the textbook, on page 45, I'll just write down the version as he has it. So I'll write this for temperature as a function of longitude and latitude. And he forgot to mention time, but that's the critical one in terms of the evolution of the fields. So we have a sum over little m, that's the x index, and then we have a sum over little n, which is the y index, and then we have the expansion coefficients, m, n, which are functions of time, and then Warner writes the spherical harmonics as a single creature, which is a function of lambda and phi. So just in case you're confused, this is the spherical harmonic. Okay, so the spherical harmonic is composed of two things: e to the I mkx as before, and that's good. It's good because we understand it, and we could do things with sines and cosines with our eyes closed. But the other piece is new, so this p sub m n piece, which is a function of mu, and mu is the sine of latitude. If I remember, I'll come back and tell you why there's a mu in there. To me, this is a Hough function. But I'll go back and look that up. Anyway, it is it's a Legendre polynomial. So in that sense, it's like the Bessel functions from earlier or the Hermite polynomials from earlier. It's a polynomial which solves Legendre's ordinary differential equation. Okay, it's just that there's lots of them. So let's have a look at how that works. So if I go back here, this thing about Hough function here, so let me think about how I want to say this. You have the sum over m and the sum over n of the weights, which right now I don't care about, e to the I k m x, which we still care about. And then when I was growing up, this would be denoted the Hough function, which is a function of latitude, okay? That thing. And the thing is that the Hough function is, I do not know why that happens. It's really bizarro. Okay, so the thing is that a Hough function is composed of an infinite sum of associated Legendre polynomials. So you begin to see the problem here with spherical geometry. Hang on, it's gone crazy again, but I can fix it now. You begin to see the problem. Let me try writing the word polynomial without falling over. In spherical geometry, the appropriate functions that we have to use in our spectral method, the functions in the north-south direction are called Hough functions, and each one is an infinite sum of these things called associated Legendre polynomials. And as I think I mentioned a couple of slides ago, what we'll do in class is pull up some Wikipedia pages. I'm not smart enough to incorporate them here, and look at that idea in a bit more detail and see what these things look like shape-wise. But in theory, we're going to have an infinite number of these to make these. And so, as I've said before, the math gets really kind of hairy when you go to spherical coordinates, but that's what we're stuck with. So let's look at what this number little n means to us. And I'm going back to, oh, wait a minute, this this. If we go back to the expression for the Legendre polynomial, so this is n and m, then m is again the zonal wave number, as it has been since the beginning of time. So that's the wave number in the west to east sense, and it's an integer. So your east-west domain could be filled up with 1 wave, 2 waves, 3 waves, 4 waves, 5 waves, 6 waves, all the way up to capital M waves. Now, the quantity little n is called the total wave number. And so what that leaves is that n minus m is the north-south wave number. So once we've decided to work on the sphere and use spherical harmonics for our expansion for things like UVW, pressure, temperature, humidity, ozone, methane, you name it, in a full general circulation model or in a climate model, we have to know what the parameters m and n mean. And so n minus m gives us a north-south wave number, which gives us some strength or some sense, of the north-south structure of the assumed piece P, which is just one of the pieces that goes into the picture. So let me show you a couple of examples of what the structure might look like here in our assumed piece. So let's go orange now, okay? Let's suppose that we're going to let m equals 2 and n equals 3, which implies that n minus m equals 1. So you have 2 waves in the east-west sense and 1 wave in the north-south sense. So let's map that out. 2 waves in the east-west sense, 1, 2, I think that's what we have there. This is x. Well, this is the distance L equals 2 pi over a little k. Okay, so that's the x direction. So we have, and I've just drawn simple sine waves. So there's 1 and there's 2. And that follows from n equals 2. Now, in the north-south sense, what are we looking at here? So let's turn the diagram sideways. So this goes from the North Pole to the South Pole, and we have 1 wave. So that's equivalent to having something like that, except that piece at the end shouldn't be there, okay? If this was temperatures, then this would be a warm, cold structure. And in the north-south, it would be warm, cold structure. And so you add them together, and you get something like this now on the sphere. Hang on. My sphere just went sideways. Let's try that again. On the sphere. So starting at 1 longitude, we're going to have a warm region in the northern hemisphere and a cold region in the southern hemisphere, as dictated by this. And then at the same time, we're going to have an east-west structure as dictated by the value of little m. And I can only show you, of course, half of the globe, but that's what we're looking at. So this is the North Pole, down here is the South Pole, this is the equator, and so choosing m to be 2 and n to be 3 means that on the sphere you're representing a structure that has these kind of characters to it. I did a second one. Wonder if I should try to just make a mess. Nah, I think what I'll do is just open up a second page, and I'm being a bit lazy here. If I wanted to, I could pause the recording, but why not live life to its fullest? So here's a second example, e.g. m equals 2, n equals 4, so n minus m equals 2. So in the east-west, we again have 2 waves, like so, a little bit more there. And then in the y direction, which goes from north to south like this, we now have 2 waves. So we have plus, minus, plus, minus. Okay, and now if we put them together onto the sphere, I think actually I could use a larger sphere. Starting at the North Pole, we have a positive region, then a negative region, then a positive region, then a negative region. And then going east, the opposite, because we still have a wave 2. And if you look up spherical harmonics and you look at images, you're going to see pictures like this all over the place. And I'll find some for you in on Wikipedia. Just one thing to let you know, the value of n minus m tells you about the north-south structure of the assumed piece of the problem. And people pay attention to whether that is or is not symmetric about the equator, because you have some meteorological phenomena, excuse me, meteorological phenomena which either are or are not symmetric about the equator. So that's what spherical harmonics are, and that's how they come into the problem. The last part of the question then is about truncation. And this is in terms of spherical harmonics, okay? So we're going to write that a field like temperature, which is a function of longitude, latitude, or sine latitude, it's going to be a sum over m and a sum over n of the expansion coefficients, which are functions of time, times the spherical harmonics, which, going back to the notation in Warner on page 45, is going to be given by capital Y. Don't know why it's a capital Y, but it is, which in turn is a function of lambda and mu. The east-west piece is always going to be that nice familiar e to the I kx thing. The north-south piece is the Hough function Legendre polynomial. So now we're going to do the truncation. And the truncation is to let m be less than or equal to, and again I'm using Warner here, and Warner uses capital K. Okay, so that's like saying M equals negative capital K to positive capital K. Okay, and then little n will go from the value of m. M could be negative, so we'll make it, n goes from the absolute value of m up to its own limit, capital N. So these numbers, k and n, give you the truncation. In other words, non-infinite series. And it turns out that there are two types of truncations that people use a lot. And to figure that out, let's have another screen. The first type of truncation that people use is called triangular. Triangular truncation. And in triangular truncation, we assume that capital N, hang on, we assume that capital N is equal to capital K. And there's a way of understanding this if we plot this in wave number space. So let's have this axis, which is the value of little m, going from plus capital K to minus capital K. And then this axis, no, that won't work at all. Try that again. All right, this axis, which is the value of n, and the triangular truncation means that the values that we use are contained in this space, which curiously is a triangle. So what the heck does this mean? The wave numbers allowed in the problem in the m space and in the n space are related by this idea. I'll have to look and see if that means something in terms of physically what the truncation looks like. And actually, I think there is something about that in the book, so I'll have a quick look at that and reproduce that for you. So this is one kind of truncation. I'm going to be lazy now and just cheat. The other kind of truncation is called rhomboidal. And you might be thinking there's a rhomboid in here, and you'd be right. And in the rhomboidal truncation, n is equal to the value of little m plus k. And so in the rhomboidal truncation, the geometry looks like this now. And curiously, the blue shape that I've just drawn is a rhomboid. So this is what the truncation choices are called, triangular or rhomboidal. Judging by what I've seen in my massively long career, mostly we see triangular truncation. And so you'll see, you'll read in a paper or a document that you're using a T241 model. That means it's the triangular truncation and probably K is equal to 241. Actually, I hadn't thought about what the 241 equals. This gives you an idea of how many spectral waves are involved in the problem, and T means it's triangular. And what I have written down here, I haven't looked this up for a few weeks, so but anyway, the GFS is T1534. And so it's a triangular truncation, and that's the number of waves to give you an equivalent horizontal resolution of 13 kilometers. So the ECMWF model currently is running at about 9 kilometers, so this is going to have to be a bigger number for them. Let me just read from the textbook. Let's see. Let me just write up here. This is page 45 again in Warner's textbook. He very kindly invites us to read, this is right down at the end of the page, the triangular truncation is more commonly used for reasons discussed in Krishnamurti. Thank you very much. We didn't really want to go read anything else. Triangular truncation provides a resolution that is uniform on the sphere and the same in zonal and meridional directions. So it would be the equivalent of, say, 13 kilometers east-west and 13 kilometers north-south if you're using the triangular truncation. Rhomboidal truncation produces higher resolution near the poles. So if you're a polar scientist, you might want to use a rhomboidal truncation. And that's all I have for so far, so let me end this.